Okay, so thank you very much. Let me start by thanking the organizers for giving me the opportunity to present at this meeting and to see this fantastic place. So what I'm going to present today is a collection of lattice results obtained over the years about SUN gauge theories in the non-perturbative regime, and I'll try to see what we can learn from them. Okay. So this is essentially the plan of my talk, which I could have easily entitled A Tale of Three Conjectures. Because indeed, what I'm going to do is to analyze some of these lattice results in a quite provocative way, to see whether we can learn new things, new features about gauge theories beyond the usual large N limit. Okay? So the first topic I will cover is the existence of the 't Hooft large N limit. Then I will present a recent results that we have put forward in the form of conjecture concerning this ratio in Yang-Mills theories. And then I will move to another conjecture saying that essentially Glueball mass ratios can be related to anomalous dimensions. Okay. By anomalous dimensions, I mean anomalous dimension of the chiral condensate in gauge theories with fermions. And finally, we'll conclude what we can learn from all that. Okay. But let's start with something that is somewhat more familiar, which, as I was saying, I want to present in the form of a conjecture. Certainly, this is something that I hope we can all agree upon. So what did 't Hooft say? What did he suggest? Well, he suggests that if we take the limit for the number of colors going to infinity and for the coupling constant going to 0, fixing this combination, then in SUN gauge theories, quantities are regular if we take n large. And in particular, they go in a power series of 1 over n squared in the pure Yang-Mills case, or in a power series of 1 over n if I have NF fundamental fermions. So why is all this useful, or why do we hope that is useful? Well, there is a hope that if we can really find the Taylor-Maclaurin series around n equal infinity, and we can extend it all the way down to n equal 3, then we can learn analytic lessons for QCD. Okay? In particular, we can explain some of the phenomenological features of QCD, like the OZI rules, or the fact that processes in which you go from a state with quarks to another state with quarks through the annihilation of all the quarks in the intermediate state, these are suppressed. Moreover, the large N limit is more amenable to analytic calculation. And more recently, he has connections with gauge string dualities. So this is an interesting program that one can do non-perturbatively on the lattice. I can just give an overall overview about that. I will refer you to a fairly recent review that I've written with Marco Panero on the subject, which is more comprehensive. Yeah. So what is the lattice program? I mean, we have had several lattice talks today and in the previous days. So what we do is we take a SUN gauge theory, we regularize on a lattice, and eventually we want to remove this ultraviolet cutoff. In this case, we want to vary another parameter. We want to vary n, the size of the gauge group in SUN. Yeah. So what we'll do a standard lattice calculations once we have fixed the lattice cutoff, and then we extrapolate to the continuum limit, and finally, we extrapolate to n going to infinity using as an ansatz the suggestion of 't Hooft. What I want to remark here is that the two limits actually commute, and one can see that, for instance, in the lattice strong coupling. So it is another possibility is first to extrapolate in 1 over n, and then taking the lattice spacing going to 0. For this, we have simulated a range of gauge groups from 2 to 8. And we did also a simulation at n equals 17 because there was the concern that perhaps the Monte Carlo dynamics, if you don't get a prime number, could break into some subgroups. This is technical, but that explains why you get this 17 here. Okay, so this is a typical calculations that we did at some fixed lattice spacing that we did by fixing the critical temperature as a scale. This is just a convention. I could have fixed the string tension, or I could have fixed any other quantity that I get in SUN. This is the pure gauge theory without fermions. And these are results at the various gauge group all the way down to n equal 8. And the continuous lines are a fit with only the leading 1 over n square corrections for the ground state, for the first excitation, and the second excitation. This is what on the lattice we call the A1 state, which is what in the continuum we call the 0 plus plus. Okay? So this, if you wish, when I extrapolate to the continuum limit, this will give the mass of the 0 plus plus. So what do we learn from this example? Well, what we learn is that a 1 over n square correction describe the physics, certainly from SU8 all the way down to SU2 in this case. Okay? And it is possible to determine quite accurately the large n limit of this spectrum. This is the status of the art for the lattice calculations of Glueball states at finite lattice spacing. This is a work that I've done in collaboration with Antonio Rago and Enrico Rinaldi. What we did here is a sophisticated calculation, variational calculation, including several lattice operators, so that if we diagonalize the entire correlation matrix, what we could get is a fair approximation of the wave function of the ground state. Then we can project out the ground state and get the first excitation, and until that works. Okay. So these are, I've used the lattice notations here. So again, these are the glueballs in the 0 plus plus sector. The E plus plus is what in the continuous becomes the 2 plus plus. This is degenerate with the 2 plus plus, with the T2 plus plus here. Because for the cubic representation, you get that the 5 spin 2 components are projected 2 into the E and 3 into the T2 representation of the cube. Okay? So this you can use also as a check to test this degeneracy of how close you are to the continuum limit. And this works reasonably well. In addition, we find a bunch of other states and excitations in other channels. To understand better the picture, it's worth remarking that these states, especially when you go to the excitations, they can mix. They can mix, for instance, with scattering states, and that's the physics, or they can mix with Torrelon states, which are finite size effects that you get on the lattice. Our operator basis was able to disentangle those spurious states and to project them out. So this is what should really be the Glueball physical spectrum of what we believe it to be. You will see also these lattice, these yellow boxes, which go back to a previous calculation that I've done in collaboration with Mike Tepper and Urs Wenger, who is in the audience, from 2004, where you can see actually the error, how the error gets reduced thanks to the sophistication in the construction of the operators. Okay. I now go back to this calculation because it's still the state of the art to these days in the continuum limit. So again, here, what I'm doing here is to take the 0 plus plus, the excitation of the 0 plus plus, which are the red point at the top, and the tensor Glueball, which are the green points, and to extrapolate them to the continuum limit. These are done for SU2, SU4, SU3, sorry, SU4, SU6, SU8. Yeah. What you will notice here is that you get a fair extrapolation all the way down for SU2 with just the leading 1 over n square correction, while if you insist on putting the leading 1 over n square correction, you can only, well, I mean, only among quotation mark, extrapolate back to SU3. Okay? So in the sense that a controlled extrapolation to SU3 works for this data, you can say that SU3 is close to the large N limit. And the large N limit is defined constructively by fitting all these observables. Okay? So this is the results that you have just seen. So what I would like to remark is that you can get the ratio of the Glueball mass over the square root of sigma in the various channels with a fairly good accuracy, which is at most order, well, I would say, well, not even, it's of the order of 5% at most, with a correction 1 over n squared that is small. Okay? So this defines your spectrum in the large N limit, and the fact that you can extrapolate back to SU3, once again, the fact that SU3 is close to large N. Right. What about the mesons? Okay. One of the byproducts of the large N à la Hooft is that if you fix the number of fermions, then the large N limit is quenched. If the large N limit is quenched, I can do the meson spectrum in a quenched calculation. So n by n, I will be getting the wrong result, but the large N limit is bound to be correct. And this is what you see here in a work that I have in collaboration with Del Debbio, Patella, and Pica from 2008. What we did is to compute as a function of the bare quark mass that you won't see on this axis, the mass of the rho and the mass of the pi. And then we have extrapolated using the leading order chiral perturbation theory to the 0 quark mass limit. So these are these lines, which fits fairly well the data from SU2 to SU6. And by extrapolating them to n equal infinity with our 1 over n squared correction, you get the black line up here, which is your chiral perturbation theory relation between m rho and m pi at large n. Yeah? This was done at the same time also by Gunnar Bali and Francis Bursa with very similar results at a slightly different lattice spacing. Yeah? This is a more recent calculation for the whole mesospectrum in the n equal infinity limit. I'm talking about the iso-triplet channel here because the isoscalar is most complex because of the disconnected diagrams. Yeah. So what I'm reporting here is our f pi, f rho, and then all the bunch of mesons that you can get, including a few excitations. The horizontal purple bands are the extrapolated large N limits, while the color-coded dots are the results of the calculations that you get at finite n. This has been done once again for a single lattice spacing, so this is not the result of any continuum extrapolation. We have done a continuous extrapolation for SU7, and we expect this to be correct, order 10–15%. So the systematics of not doing the extrapolation in this plot is 10–15%. Okay, so these are the results. You see that some states for SU2, for instance, and in general have a slower approach, while others have a pretty fast approach. For instance, the mass of the rho. This will allow us to give a first comparison with QCD, where you fix the scale from the f pi at infinity, and you fix the mass of the quark by imposing that the pion is at the physical point. If you do that, this is what you get, where now the dots indicate the experimental points for those states, while the bands are our calculations. What emerges is that our calculations actually are pretty much in agreement with the QCD spectrum for the fundamental states, or whenever you see a blue band, where the excitation seems to be a little bit far off. Whether that is systematics related to the extrapolation, whether that is systematics related to the extraction of the excited states, or whether that's the physics, at this moment, we cannot really comment. Okay? But anyhow, what else do we learn? Well, we learn, as I say, that some of the states are actually remarkably close, well beyond the expected 1 over n error that you might think is there. There are also degeneracies at large n that you do not observe in QCD, but they are predicted by chiral perturbation theory. For instance, one is the degeneracy of the rho and the naught that we can see here in between these two bands that is emerging at large n. Okay, now let me move to the second part of the talk. And let me move to the second conjecture. So what's the second conjecture? So let's go back to pure Young-Mills. So the conjecture is that in pure Young-Mills, if you take the mass of the 0 plus plus squared over the square root of sigma, this is proportional to the ratio of the Casimirs, with the proportionality constant actually depending only on the dimensionality of space-time and nothing else. So you will get the same law in 3 dimensions and in 4 dimensions with a different eta. And this is true whether you have SUN, whether you have SON, or whether you have SPN. So that's the idea. Okay? Why is that relevant? Of course, I mean, if you get such an universality, I mean, universalities are always powerful tools. So if that actually turns out to be the case, then you really learn something about the non-perturbative physics of Young-Mills theories, and you really learn something about the mechanism, potential mechanism of color confinement. So what do we bring as support of this conjecture? Well, the first evidence is from lattice data on Glueball masses, and then there are a few heuristic arguments that are based on analytic calculations that actually suggest the same thing. This we have reviewed in a recent work. Let me start from what the lattice seems to suggest. What we have done here is we have put together the latest results of the simulations of SUN gauge theories and SON gauge theories in the large n limit. And these have been plotted against the conjecture. So essentially, we have identified this eta, which I will talk more about in the following slide, and we see how well the data go with the Casimirs. This is the picture for the SUN in 3 plus 1 dimensions, and these are the triangles, which have larger errors, and in 2 plus 1 dimensions, which give even a cleaner picture, and these are the boxes. While the SON series comes from below, and all of them converge to the ratios of the Casimirs at large n, which is actually 2. Okay. We also have a check for SP4 that we have to simulate for different reasons, and also SP4 as an eta compatible with what you would extract here. Now let's do the reverse, and let's see what this eta is. Okay. So these are the fit once I subtract, well, once I normalize by the Casimirs this ratio. And what I find with a visual precision of the fits that you can check from the figure is that the eta turns out to be 5.41 in 3 plus 1 dimensions, and it turns out to be in the region of 8.4 in 2 plus 1 dimensions. In 2 plus 1, we have also more calculations and more precise calculations. So by differentiating between the SUN and the SON series, we were able to find also the systematic errors in our fit. Well, what are the arguments that actually support this conjecture? Or if you wish, why did we get the inspiration to do the analysis? In fact, there is more than one. One of them is based on a variational calculation of the ground state in 2 plus 1, for instance, in this work, and in which you get actually that law that I've showed in the previous slide. Then another model that you can make is to treat the gluon pretty much as in the Glueball, pretty much as you would treat the quarks in mesons. This is called the constituent gluon model, and has been pushed by the group of Buisseret or in other collaboration by Bicuto and many others. And this will give you the same results. In our work, we have presented 3 different arguments. One is based on a Bitten-Salpeter calculation. Another one is based on some rules. And the third one is based on the interpretation of the Glueball as a dilaton, which actually saturates the dilatation anomaly. Yeah? When we published the paper, we received also an interesting email by Jeff Greenside, who has reproduced essentially the same argument in the Coulomb gauge in an Hamiltonian calculation. Okay, so it would be nice to have either more evidence or, a falsification of this argument, which I believe it's quite powerful. What happens if we move to other states in the spectrum, you may wonder. Yeah? So what we could do is to analyze, for instance, the 2++, and you will see that the picture is pretty much mixed. There is some, there are some indication that actually the scaling can be true if you move to larger n, but is certainly violated at lower n in 2+1 dimensions, when in 3+1 dimensions is pretty much fulfilled. Let us analyze the issue in a different way by proposing the ratio of the 2++, the mass of the 2++, over the mass of the 0++. I'll see that these points can be fitted by a constant with a reasonable chi-squared, and the constant turns out to be 1.41 with an error of, say, 2.5 in the last digit. Okay? Which brings me to an even bolder conjecture. So is actually this ratio universal in 4 dimensions, and is it square root of 2? There are, for instance, ADS-CFT models that predicts that to be the case. There are other ADS-CFT models that instead get a different ratio. Then you can also analyze the case of the first excitation in the 0++ sector, and you see that there is no indication of any form of universality whatsoever, which is nice in another respect because it means that actually when you can see it, you can really see it. Okay, and now for the last part of my talk, I will switch slightly the context, and I will move back with theories with fermions, but now I'm interested also to change the number of fermions and to see what happens when I approach the infrared conformal phase of the theory. So what is the conjecture in this case? So if I take asymptotically free SUN gauge theory with NF fermions in the fundamental or 2x index irreducible representation of the gauge group, then the anomalous dimension of the fermion condensate is a monotonically increasing function of the quantities that you will not expect. The ratio of 2 Glueball masses, the 0++ and the 2++. Okay. What we have done to support that is, okay. So what we have done to support that, we'll sort out that error later on, is to take some lattice calculations and to compare them with some gauge string duality results. And this is reported in a work that I have with collaboration with various people, including Georg Bergner, who is in the audience. Okay. Let's see now how far we can go here. Okay. So let's forget about the effects and let's show everything. So what's the context here? Well, if I varies NF, QCD is a theory with low NF, essentially. So in QCD, you get confinement and chiral symmetry breaking. In a line in which I plot the phase of the theory as a function of NF, you will be sitting somewhere here. I know that when I increase NF up to a limiting point, I will lose asymptotic freedom. And for the context of this talk, I'm not interested in that. And what Banks and Cancher have conjectured is that actually, before that happens, there is a phase in which the theory is infrared conformal. That's what we call the conformal window. For phenomenological reasons, it is also interesting to see what happens on the seal of the conformal window. that can be related to BSM theories that explain the Higgs as a composite state. So what I'm doing now is to see what happens to the anomalous dimension of the condensate, which is the quantity that that is the quantity that theorists that aim to understand BSM physics concentrate as a function of the global masses. So this is what you get in a gauge string duality model, which is the GPPZ model. What you get here is, this is a calculation that actually takes the matrix and extracts by fluctuations of the matrix in the standard way the global masses. What you'll get is that the 2++ glueball monotonically increase with this number, which is 1 plus the anomalous dimension of the condensate. Why did we take this model? Well, the only reason that actually we focus on this model is that this number here appears as a parameter in the model itself, and we can vary it. What happens when we put the theory on the lattice? Well, on the lattice you have to be careful, because you break conformality if it's there in many ways. So ideally, this is the beta function that you should reproduce. In practice, well, in practice what happens is that you always have to regularize with some mass, which means that in the far infrared you will always run into a confining theory. And if you are not careful enough and you take too big a mass, then you really see no remnant of conformality whatsoever. And on top of that, you have also an infrared cutoff, which is your box size. So what we are doing here is to reanalyze lattice calculations that were not designed explicitly for that, and to compute this ratio as a function of the box size, mindful that as the box size varies, we can be either in the asymptotically free phase, which is uninteresting, or we could hit another phase we are not interested in, which is the confining phase. Okay? So this is the results that we got for SU2 gauge theory with 2 adjoint fermions. So what I'm plotting here is the SU2 Young-Mills value for this ratio of the glueballs, which you have seen before. And these are the lattice data. So what you find is that if you take the lattice big, then you go into the infrared confining phase because of this mass. If you take the lattice small, this is dynamical. That's crucial. So if you take the lattice small, then you go into the finite size effect that you are not interested. But there is an intermediate region that gives actually a sign that you are touching the prediction of the GPPZ model. Okay? And a similar thing goes on for the model with 1 adjoint flavor. I should have remarked that the anomalous dimension was measured here, and this is what we took here to draw this pink band. That is the value that you get for this anomalous dimension from the GPPZ model here. Okay? Right. If you take 1 flavor, lattice calculations that we have done again suggest a value of the anomalous dimension that is of order 1. And again, that unless you go far into the infrared regime, you see that actually you are converging to this ratio. And this number 6 is interesting because it's actually a high number that you don't get in the other model. And another thing that I should have remarked is that there are arguments that limit this delta to 2, and it's interesting to notice that actually this model predicts a divergence of this ratio 2, indicating that essentially the glueball becomes an exact dilaton. Right. So I think that brings me back to the conclusions. So I have presented a set of lattice results related to 3 different topics with the hope that will provoke some thoughts and some reaction from the audience. One is related to the construction of the large N limit a la Hooft. The other is related to an universality that involves the 0++ glueball and the string tension. Part Passing by, I've also remarked that there could be another universality between the ratio of the tensor and the scalar glueball, for which we have much less evidence and which I will not insist too much. And finally, in theories with fermions in the fundamental to index representations, there is this nice connection between the chiral condensate anomalous dimension and the ratio of the tensor over the scalar glueball masses. Okay? So what will be interesting to do? Well, obviously, especially in the last part, these calculations were not designed for this purpose, so we have very, very limited evidence. So if you want to push this conjecture, one will have to design calculations that are fit for this purpose. Okay? It would be also nice to obtain confirmation or disapproval from analytic arguments of any type. If these universalities turn out to be more robust than we think, then it will be interesting also to understand the mechanism that determines them. And finally, an interesting question is whether actually are they exact or are they approximate? Are they some leading order in some quantity? Okay? And this will be also another question that we might want to find an answer to. And with this one, I came to the end, and thank you very much for your attention.
Questions? Okay, I see no questions, so let's thank the speaker again.
Thank you.